Good evening, everyone. I'm Anish Becker, PMRF and PhD candidate from Aerospace Engineering, ISC Bengaluru. Welcome to this week's live interaction for the NPTEL course, Dynamic Behavior of Materials. The course code is NOC24ME102. This is part of the weekly live interaction session. So, as is the custom, we'll go through a few concepts as well as some associated problems to try and elucidate all that has been taught in this week. So an outline for this particular session would be, we'll be first going through the general solution for a wave equation. Then we'll be specifically looking at our problem of interest, which is elastic wave in a cylindrical bar, what practical considerations are also involved. And then we'll be moving towards plastic waves part of the course. So a general equation. Suppose we have already seen in the case of like a vibrating string, we can write equation of motion as rho square y by dou t square. This is my vibrating string, y being the displacement along y-axis. This can be written as something like t by rho square y by dou x square. Similarly, we have seen in the case of a spring, we can write the wave equation as rho square s by dou t square equals k by rho dou square s by dou s square. Here st is the displacement of a small spring section. Same thing we have seen for elastic wave in a cylindrical bar, which looks like rho square u by dou t square equals e by rho dou square u by dou x square. This is equation for an elastic stress wave in a bar with a thin cross section. We have also looked at longitudinal wave in an unbounded medium. Longitudinal wave, it has the expression dou square delta by dou t square is lambda plus 2 mu by rho dou square delta by dou x square, where delta stands for dilatation and is given by the equation delta is equal to epsilon ii. So this is nothing but epsilon 11 plus epsilon 22 plus epsilon 33. So change in volume for an infinitesimal element. If we think of this in the form of a general second order PD, what we end up is a dou square by dou x square. It should be grad square plus p times dou square dot by dou x dou t plus c times dou square variable with respect to t and some other terms going to 0. So this is like a general second order PDE, partial differential equation. From this we can determine different types of partial differential equation by calculating b square minus 4ac. So this is similar to discriminant calculation. If this is, I'll write this as delta PD. If delta PD is greater than 0, call this a hyperbolic equation. Delta PD equals 0, we call it parabolic equation. Delta PD less than 0, this is an elliptic equation. So this is a general classification of PDEs. And why is this important or relevant to our discussion? Because wave equations are generally of the form hyperbolic equations, and for to solve hyperbolic PD, solution for the hyperbolic PD can be considered in the form of separation of variables. And there is another method called as characteristics, method of characteristics. So if I were to look at my first equation, dou square u by dou dou square y by dou t square is equal to t by rho dou square y by dou x square. And if I assume y of xt is equal to capital X of small x and capital T of t. Once I substitute this into the equation, what I get is capital X into t double dot is t by rho x double dash t, and I'll continue it in the next page. So we have capital X of x into t double dot of t is equal to t by rho. This t will be confusing. I'll just rewrite this as C naught square. This is tension, and this capital T is a function of time. We'll be using this form of equation. So you have C naught square T in T of T into x double dash of x. From this, if I move around my variables, I have x double dash of x, C naught square, x double dash of x upon x of x is equal to 1 over C naught square T double dot of T by capital T of T. So on the left hand side, you have something which is an equation of x, and on the right hand side, you have something which is equation of or a function of t. For both of these to be equal, the only solution is when they are both equal to some constant. X double dash by x is equal to 1 by c naught square t double dot of by t, say some constant lambda. From this, now you can, like the procedure is straightforward. X double dash is lambda x and t double dot is equal to c naught square lambda t. T double dot of t is c naught square lambda t of t. From this, the procedure is straightforward. This basically both of these equations look like they are derivatives of exponential function. So you could write capital X of x as say some a e raised to root lambda x plus b e raised to minus root lambda x, capital T of t as c e raised to c naught root lambda t is t raised to minus c naught root lambda t, which would basically give you y of xt is equal to a e raised to root lambda x plus b e raised to minus lambda x into c c naught c into e raised to c naught root lambda t plus t into e raised to c naught lambda minus c naught root lambda. So you could write a general expression of this, and then to find out the exact solutions, you will require both initial conditions and boundary conditions. Just substitute them and then you can evaluate what the particular value of constants A, B, C, and D are. Another way to solve this was given by D'Alembert. So we have already looked at it in the class, but I'll just go through the steps once before numerical example. Suppose you suppose our wave equation is of the form dou square u by dou t square c naught square dou square u by dou x square. So we in D'Alembert solution, what we do is we replace our original variables, which are x and t, with some new dependent variable. Say epsilon is equal to x minus c naught t, and eta is equal to x plus c naught t. Okay, then we can write small change in u is dou u by dou epsilon d epsilon plus dou u by dou eta d eta, which should give you dou u by dou x is dou u by dou epsilon by dou x plus dou u by dou eta by dou x. Dou epsilon by dou x and dou eta by dou x can be evaluated based on our chosen form of the variable. So they basically are one each. So you end up with dou u by dou epsilon plus dou u by dou eta, which can be written as dou by dou epsilon plus dou by dou eta of u. So if I take the second partial derivative of u with respect to x, I end up with dou by dou epsilon plus dou by dou eta of dou u by dou epsilon plus dou u by dou eta, which gives me dou square u by dou epsilon square plus 2 dou square u by dou epsilon dou eta plus dou square u by dou eta square. Okay, next, if I take partial derivative of u with respect to t, I end up with dou u by dou eta mine into dou eta by dou t plus dou u by dou, sorry, this should be eta, dou u by dou eta by dou t. This would be basically minus c naught, and dou eta by dou t should be plus c naught. So you have got c naught minus dou u by dou eta plus dou epsilon plus dou u by dou eta, which can be written as minus c naught dou by dou epsilon plus dou minus dou by dou eta of u. Therefore, the second partial derivative of u with respect to t would be minus c naught dou by dou epsilon minus dou by dou eta into minus c naught dou u by dou epsilon minus dou u by dou eta, which is this minus c naught minus c naught. If I remove it out, it would be c naught square, and then taking this and derivating the last term, we end up with dou square u by dou epsilon square plus, minus 2 dou square u by dou epsilon dou eta plus dou square u by dou eta square. If I use equations 1, 2 and 3, if I use 3 and 2 equations in equation 1, what I end up with is dou square u by dou t square minus c naught square dou square u by dou x square equals 0, which is nothing but c naught square times dou square u by dou epsilon square minus 2 dou square u by dou epsilon dou eta plus dou square u by dou eta square minus c naught square, c naught square into equation 2 gives us dou square u by dou epsilon square plus 2 dou square u by dou epsilon dou eta dou square u by dou eta square. This is 0, so you end up with these terms cancel out. So I end up with 4 c naught square dou square u by dou eta equaling 0, which is nothing but dou square u by dou theta dou eta equaling 0. So this is what the substitution of variables gives us D'Alembert solution. If I want exact solution, what I would do is integrate this. First integrating with respect to eta gives us dou u by dou eta is square u give you dou u by dou eta to be some function, say some h of theta. And if I again integrate this with respect to theta, I end up with dou u by dou theta is equal to u, which is nothing but h of epsilon d psi, which can be, since this is a partial derivative, we have to now account for a function of the other variable. So you end up with, say, something like f of x theta as the integration of this plus some constant term, which is c of theta. So your overall solution looks like u of xt is u of psi eta theta eta, which is capital F of g of, which is nothing but capital F of x minus c naught t is capital G of x plus c naught t. This is how your general solution looks like. This capital F part is your forward propagating solution, and capital G part is your backward propagating solution. So why is this forward propagating? Because you can see that as time t increases, for x minus c naught t to remain the same, so like the phase of the particle to remain the same, capital X also has to increase, which means it's a wave, which means a particle which should lie on the right hand side, towards the right hand side, towards the positive x axis, would eventually be disturbed, and thus that's a forward propagating, positive x axis propagating wave. Capital G, invert the logic, as t increases, for x plus c naught to remain the same, x has to decrease, which means a particle on the left hand side of the original disturbance will now be in the same phase as, say, the original uh, particle, or the original disturbance of the original particle was, which means that the disturbance is now propagating from the origin to the left hand side. So it's a backward propagating wave. Yes, go on.
just now you have defined the two uh, two direction of the wave propagation.
Yes.
So is this concept valid for the special type of uh, loading, or we can say special type of disturbance to our system, or what it exactly means?
So I think like I'll just simplify this. What it's not like too complex. Think about it this way. Suppose I have a rod like this, and in which on the top of this I provide a disturbance to it. Then the disturbance in the rod will can propagate like in every possible direction to which the rod exists. So since this is a one-dimensional object, you can have the disturbance propagating ahead of where I provided the force as well as behind of it.
Okay.
Like no need to to- the easiest way to think about this is both those x plus c naught t and x minus c naught t are simply like directions where the energy can or the disturbance can propagate. That's it. If you have a three-dimensional object, you can have wave going from point A to point B as well as from point B to point A.
Okay.
One thing that I wanted to show was in this D'Alembert solution itself. Suppose we are given an initial condition which is of the form suppose y of x comma t equal to 0 is equal to y naught of x and y dot of x comma t equal to 0 is y naught dot of x. If this is say an initial condition that has been provided, then from this what we can get is at t equal to 0, if I rewrite my solution y of x, if I rewrite my general solution is capital F x plus c naught t x minus c naught t plus capital G x plus c naught t. At t equal to 0, you have y of x is equal to capital F of x plus capital G of x and y dot of x being minus c naught capital F dash of x plus c naught capital G dash of x. So we simply substitute these equations here and what we end up with is capital F of x is capital G of x is equal to y naught of x and minus c naught times capital F dash of x minus G dash of x is equal to y naught dot of. If I integrate this, if I integrate this second equation, what do I get is end up with f dash of x minus g of x going from 0 to x is integral minus 1 over c naught y dot of x dx going from 0 to x, which is nothing but capital F of x minus capital G of x is capital F of 0 minus capital G of 0 minus 1 over c naught integral 0 to x y naught dot of x. So using equation 1 and equation 2, you can figure out capital F of x is equal to y naught of x by 2 minus 1 by 2 c naught integral 0 to x y naught dot of s ds and capital G of x is 0 minus G of 0 by 2 y naught dot of x by 2 plus 1 by 2 c naught equals 0 to x s ds plus sorry minus f of 0 minus g of 0 by 2. So using D'Alembert's equation, we are able to convert, we were basically able to go from PDE, then variable substitution. This is psi times xt, and we ended up with a solution is sum of two functions, which are capital F and capital G. So once you apply the appropriate initial and boundary conditions, we can figure out what our exact solution looks like. Here, even though on the left hand side I'm using the variable x in both capital F and capital G, it does not necessarily relate like the displacement x. This is just talking about the function capital F and function capital G. So, so once you have x, you can convert them to zeta eta by the relation x minus c naught t and x plus c naught t, and then plug those into capital F and capital G to obtain your general solution at the point x comma t. An example, I'm not solving this, but an example of the same could be, suppose you have a string like this, should be symmetric, sorry, should be symmetric. X is equal to minus L, x is equal to plus L raised to a height y, and then the string just goes on. It just goes on till infinity. If this is your condition at t equal to 0, and there is no initial velocity, so no initial velocity, only initial displacement. So what if I have to write, what I would write the initial condition as y of x equal to 0. This is y naught of x is a into 1 plus x by L, when minus L less than x less than 0, a into 1 minus x by L, and 0 x L, and this is 0 otherwise. So this is my initial condition. Once I plug this in and solve for capital F and G, what I see as the solution as two, the solution ends up being two distinct ways. So I'll just, so the solution at say some different time will look something like this. At 2, this is the forward propagating part, so this is capital F of x minus c naught t, and this is the backward propagating g of x plus c naught t. Use this particular initial condition and plug this into the equation, plug this into this equation to obtain what your general solution looks like. Here we have assumed, or rather chosen, capital F of 0 minus g of 0 to be 0. Okay, So this is how the D'Alembert's equation would be. As we can use that to obtain a general solution. Okay. Next part of the lectures was on elastic waves in cylindrical bar. Specifically, it dealt with how we analyze the impact on the bar. So, if I have a projectile, this is my projectile hitting with the velocity v on a cylindrical bar. This is my target T. Target T is a cylindrical bar with properties as rho naught, E naught, and C naught as my speed of sound. We already know that the equation for elastic wave in cylindrical bar is given as rho square u by rho t square is E by rho naught rho square u by rho x square. Okay. Projectile we also again assume it to be a cylindrical bar with same density, area, and speed. What happens at t equal to 0? Equal to 0, there is impact. Due to impact, there are some stresses generated at the interface in both projectile as well as the target. So, stress generated on impact in both bodies. Because of this, a stress wave is released. Suppose T is equal to T1. This is impact at T equal to T1. There is a compressive pulse in both. So compressive stress pulse in both target T and projectile T. I'll just extend this stress that is seen here, shade it out. Both of these travel with velocity c naught. So elastic wave front travels with c naught speed. In both now upon impact, both the projectile and uh, target experience compressive stress. Elastic wave will propagate. Elastic stress wave will propagate. Both of them have the same material and the same cross section, which is why they both have the same same speed for the elastic wave, which is c naught. At t equal to t2, happen is this compressive pulse in the target, in the projectile rather, reaches the free surface. Stress wave in target in projectile reaches free surface. So this free surface is touched, and as the name suggests, there is no loading on the surface. So if a compressive wave is or a compressive stress is traveling towards that surface, the moment it touches that surface, a tensile stress is also generated to balance that out, because the surface is free, it has no stress. So a tensile stress is generated here, which is basically your release wave. Tensile stress generated to balance compressive stress at the free surface. This is basically your release wave. So the release wave starts off from the free surface, and now that a little while ago when we were discussing that a wave will propagate in forward or backward direction, you can understand that because there is no material on the left hand side of the free surface, there is no material here on the left hand side of the free surface. The only way for this disturbance to propagate is on the right hand side. So the release wave that we see will move towards right. I'll recap once again. After impact, there was material on both left and right hand side of the surface. So a compressive stress wave was generated, and it started moving on the right hand side inside the long cylindrical bar at target, as well as in the left hand side into the smaller projectile. Then the compressive stress wave inside the projectile reaches the other surface, which is the free surface, causing a tensile release wave to start off from that point, which basically gives a release wave moving only in the right hand side, because there is no more material left on the left of the free surface. So at t equal to t3, this release wave starts off from here, and which will balance out the stresses, is basically seen moving like this. This is my original impact surface. This is my C naught. This is my and this is my release wave. I write it in short as REW or RLW, RLW, release wave. So this whole packet of stress now basically moves forward into right hand side till say it encounters another boundary. And what we can also see from this is, like at t equal to t2, you can see that this whole thing forms my wavelength, this whole section. From the time, the there is a release wave coming from back with the same speed c naught, and then there was the original wave after impact going into the right hand side of the material. So this creates that packet, it creates my wave, that basically creates my wavelength of the total system. So I get my wavelength of the system as twice of LP, where LP is the length of the projectile. So if I now, yeah, go on.
On the free surface,
Hmm.
as you just told that uh, a tensile nature wave has been developed.
Hmm. A
So,
release.
yeah, release wave. So
Hmm.
when tensile wave is developed at the free surface,
Hmm.
then after what it will do, means this tensile wave, what it will do.
So uh, okay, we'll go little deep into the free surface. So suppose this was my origin. I'm only talking about the projectile here, okay? And this is my free surface. So at free surface, we know that there is no loading. So your stress at the free surface should be zero. This is my original impact wave, original wave. I'll write it as OW for impact, coming out from impact. Once it touches this free surface, to balance out this additional compressive, to balance out this compressive stress, a tensile stress will be generated here at the surface.
Okay.
Then what would that tensile stress do? That tensile stress, write this as compression, that tensile stress, suppose T, that tensile stress will now start traveling again into the material.
Okay. Okay.
So that is why you sort of have this release wave coming up right after the compressive wave. So that limits the amount of material that will be experiencing deformation at any given instant. The length of that material which will be experiencing deformation at any given instant is given as lambda is equal to 2 into LP, where LP is the length of projectile. Now, I want you to go a little ahead with this and think of a different case where you have a projectile P impacting a target T, but now those two have two different properties. Suppose you only suppose the area is still same. You have rho 1, A naught, and C1. Now, what would happen? If again at T equal to 0, if I take impact at T equal to 0, so this is different material, same cross section. At impact at T equal to 0, what would happen is again a compressive wave will be seen in the projectile and the target. Both of them will travel. Then at some T equal to T star, this compressive wave will hit the projectile free surface. So you would have target P, projectile P. The compressive wave has already reached the free surface, and simultaneously some distance will be covered by this elastic waves C naught. This is C1. So the time that will be taken T star would be LP, length of the projectile, upon speed of wave inside the projectile. Then a release wave will be formed here, and then at T equal to say 2T star, that release wave will successfully have completed coming out of the projectile and reach the impact surface, wherein now again it will be 2T star plus some additional time delta will take. So this will again start traveling with C naught. And now how do you determine the length? You determine length of this section using this time T star. T star T by C naught, which is also same as uh, this distance covered is, suppose I call it X, or I'll call it LT, distance covered in target, LT by C naught. So you can just figure it out and say that LT is C naught by C1 times LP. And then lambda would be twice of this distance, so 2LT, which should be twice C naught by C1 LP. So like like a very simplified analysis, but you can think of this scenario in different ways. You can also say, ask yourself what would happen if the cross section changes. I think already covered that change in cross section part in I think last week final example was the same thing where you have two different cross sections coming up. So why this different material thing is important is in the case of a as well as the different cross section. In the case of a split Hopkinson bar experiment, what you would normal have is a high strength steel HSS transmission bar, then a smaller sample, and then another bar to take the energy. Should be I think incident bar. This would be transmission bar. Both incident and transmission bar are usually made out of high strength steel, whereas this small object is what you want to measure. So you now suddenly have an impact problem with both change in material property as well as change in cross section. Right. So we'll continue with the same cross section, the same material analysis. Net projectile T, target T, and what I'll do is basically use conservation of momentum. So my initial momentum was rho naught A naught L projectile into V, V being the impact velocity. After impact, I have rho naught A naught. My lambda is the amount of material being disturbed at uh, any point in time, and to say particle velocity UP. So if I flip things around, I get UP is equal to V LP by lambda, but we know that LP lambda is nothing but 2 LP by 2 LP, which is V by 2. So this tells me that particle velocity in target is half of impact velocity. So another thing is, if I look at the stress generated is rho naught C naught UP, which is nothing but rho naught C naught V by 2. So V by 2. This also we have seen, this is nothing but the acoustic impedance. We have already seen this in the previous class. This is the particle velocity. So this gives us a relation between stress generated and particle velocity as well as the inherent material property. So suppose you have a case where, sorry, suppose you have a case where you know that the particle velocity v is 30 meter per second, and then you have run out aluminum, so 2700 kg per meter cube. Velocity is 1500 meter per second. This is like aluminum rod. Then you know that the particle velocity after impact. So an aluminum projectile, then aluminum rod, target, both aluminum. Then you know that after impact, particle velocity in target T is UP is P by 2, which should be 15 meter per second. Yeah. Another thing is the stress generated would be 2.710 cube into 5.110 cube into 15, so which is around, this is a pretty large value, which is around 206. megapascal. Okay, new theoretical numerical example, not exact. There are also some practical considerations. Here are two specific considerations here. First is your Poisson effect, which involves radial inertia, and second is free surface, which involves cylindrical surface of the rod being stress free. Right. So, if we look at the Poisson effect part, suppose a compressive wave is traveling through a rod. So this is like the simplified case. And if you account for Poisson effect, what you would have is small expansion along the radial direction. Real case. So here you have radial expansion, or rather the transverse expansion with axial compression. So suppose my diameter was D and section length was delta x, then before wave passes, and then there is a change in shape during compressive stress wave. This would change to delta x into 1 plus epsilon. This will change to d times 1 minus nu epsilon. So what I mean by this during compressive stress wave is that this delta x lies inside that lambda that we have seen, like the section of the bar that is excited at a point in time. And here I am writing the standard expressions 1 plus epsilon and 1 minus nu epsilon. For compressive case, you know that epsilon. Sorry. For compressive case, we know that epsilon less than 0 for compression. Once you plug that in, this delta x, this thickness would decrease and the diameter of the cross section would increase. So in here what happens is radial expansion this is seen, but this is delayed due to inertia. That is, as long as you have a mass somewhere, that inertia would take some time uh, for say the force stress to transmit for the effect to come out. So there will be an expansion, but it will be little delayed. And another one was the free surface. Oh, I forgot to add this. So C naught is equal to root of E by rho is my wave's velocity for a 1D uniaxial stress. If I write say Cp for the 3D case, so all three dimensions considered for the rod, and then if we evaluate what velocity or stress wave has, that is the Cp, then we can figure out a relation between Cp and C0 as 1 minus 3 times nu square pi square a by lambda whole square, where a is the radius of this rod. So this is basically your Rayleigh's prediction, and it's only accurate for a by lambda less than 0.1, which means like a very thin rod. So we know that lambda is related to the length of the projectile. So imagine the projectile to have a very thin radius. A more accurate prediction for Cp by C0 is given using a more accurate prediction for Cp by C0 is given using more accurate expression by Pochamer and Shree. So the exact plot for this has been taught in the class as well as it's in the Mark Mayer's book. But the key takeaway is that there are some analytical expressions to help figure out uh, what the actual velocity would be in case the bar isn't, in case we account for the radial inertial effect and if the bar isn't like very thin. Next up was the free surface effect. So what we have here is, as a stress wave is formed and it starts traveling through the material, this front interacts like even if the impact occurs on the surface, as this stress front moves forward, there will be some interaction with the free surfaces of the rod that would in turn create release waves of their own. So this free surface creates release waves of its own. Were I to plot this t at t1, if I plot it at another time t equal to t2, would see something that it's like this also C naught, this also C naught equal to T2. So release waves coming down from the surface. As we go ahead and ahead, what see is these release waves follow the main elastic wave and they continuously interact. This causes changes to UP, changes to particle velocity UP, also leads to fluctuations in stress and strain observed inside the target. So if I plot it at another time step, this is C naught, and now you can have select multiple releases coming up, right? These fluctuations that are caused are basically seen in the form of stress profile. So suppose I were I to plot the stress profile, my ideal profile would look, my idealized, this is stress versus time. My idealized profile would look something like this. This is in keeping with our analysis, which we have seen. This is in keeping with our analysis, which we have seen, wherein a bar with velocity Vp impacted. projectile with velocity v impacted a target with which was initially stationary. And if I draw this is my ideal case, ideal stress profile. If I now include say the inertia effects, but as well as more importantly the free surface effects, what I would get is something like this. So this is my real stress profile. So when we perform split Hopkinson bar experiment, will be we do not get like an exact rectangular uh, stress pulse, stress profile. We get something with oscillations. And we already discussed that these are accounted for by understanding the role that the free surface plays in this experiment. And the radial inertial factor would cause effects on, say, the time of arrival or any delay that we see. Okay, so third part was this plastic waves. So we have already seen that once, so from the initial analysis in the last week, we looked at this equation sigma is equal to rho CUP. Acoustic impedance defined by rho C. There is a relation between particle velocity UP and stress. So we have particle velocity UP and stress sigma related by they are related to each other. And what this tells us is, suppose if my impact, suppose my suppose the projectile P impacts target P with high velocity capital V, which implies UP will be higher, which also implies that stress sigma will be higher. Now, why is this relevant? Why the you could have cases wherein the impact velocity is high. It's pretty like it's pretty self-explanatory that a lot of sorry, not self-explanatory. If you look around into a lot of examples that we have discussed in the first week, suppose like a very far-fetched example is like a micrometeorite hitting a satellite. It will be traveling like very fast, and the moment it hits it, what from this equation what we can say is that because it has a high impact velocity, there will be a high particle velocity associated with it, and that in turn would result in a high stress inside the target. This is important because usually materials will have, if we look at the stress strain curves, they will have a yield point at some, especially in the materials which exhibit ductility, there will be a yield point. So if I plot the stress strain curve, it would have straight line with Young's modulus E, then a small slope, and then you have your, this could be your yield point sigma y. Once it goes beyond this yield point, plasticity sets in. So could have a question something like this, and then making and so on. Okay, there are various ways to draw up materials. So I'll just constitutive loss. Simplest one in plasticity is the bilinear elastoplastic model. This is E1, this is E2. This is called as the bilinear elastoplastic. You can also have something that is a power hardening law. Sigma is equal to sigma naught Sk epsilon raised to n. This is the power law work hardening. Could have another type of material constitutive law, sigma epsilon. And be written as sigma is equal to sigma naught plus k epsilon raised to n, epsilon dot raised to n. This is strain rate dependent. This is epsilon dot 1, this is epsilon dot 2. So in all of these plots, the important point is once you exceed your yield point, you essentially have to account for the plastic. You enter the plastic region for which you need to have a constitutive relationship. So these three types are just showing you one of how different types of them rather would look like. And we'll now move into the one Kerman and do his experiment, and then we'll come back into the expression. This is the one Kerman. Okay, so how does this is for plastic wave in uniaxial stress. So to generate plastic wave, we talked how stress needs to be beyond the yield point, which means that your velocity needs to be sufficiently high. So the simplest setup is as follows. You take a long thin rod, you take a long thin rod, attach it to a rigid plate, this is the initial position, P less than 0. There is a weight W, this is the weight W, and it is attached to the ground using a say rubber band or a spring. Rubber spring. Why is it attached? This basically accelerates the weight to high speed. And this is your very long thin wire for which we are interested in studying plastic deformation. What happens is this weight will drop, and suppose it reaches the plate. This is the weight W. This is my rigid plate. This rigid plate will start moving down with a velocity V1, and this is my thin rod. For the label this is X. This is my thin cross section, delta X. Inside this thin rod, the particle will be moving downward with a velocity, say particle velocity UP, but you essentially have stress wave which is going up. So your stress wave is going up with say some velocity c. You have got tensile wave going upward, which basically means particle velocity downward. So I think in the first or second class we have looked at how compressive stress wave and when we have a compressive stress wave, the particle velocity is in the same sense or same direction as your stress wave direction. If now I look at the small section of wire, let u of t be the displacement of thin cross section at location x and time t. Then for this thin cross section we can write acceleration as dou square u by dou t square into the mass, which is rho naught dv, which is nothing but rho naught a naught dx dou square u by dou t square. This is change in momentum, and what we have here is the tensile stresses acting on both faces of this thin cross section, sigma and sigma plus d sigma. Therefore, you have sigma plus d sigma a naught minus sigma a naught rho naught a naught dx dou square u by dou t square. Cancelling out a naught and rearranging, so we get d sigma by dx is rho naught dou square u by dou t square. We know for the case of for 1D uniaxial stress, you know that sigma is equal to E into epsilon, and epsilon is dou u by dou x. Substituting this, you get E, oh, sorry, not E. Uh, here, here, sorry, this is my mistake. Here we are basically dealing in the plastic regime. So if I draw sigma epsilon plot, it could look say something like this. At low velocities, we might be at the stress experienced by the target might be here, which should give it say sigma is equal to E epsilon. Whereas at high velocities, you could have stress being experienced in the plastic region. So we can write d sigma by dx is equal to d sigma by d epsilon to d epsilon by dx. We still don't know what this is, but we know that epsilon can be written as du by dx for this one d uniaxial stress case. So you have d sigma by d epsilon dou square u by dou x. Combining this, you essentially end up with dou square u by dou t square rho naught dou square u by dou t square is d sigma by d epsilon dou square u by dou x square. This is familiar to all like equations that you have seen. You have an inertia term and you have a term representing stiffness. So if I move this around, I basically get my plastic wave velocity as P plastic is P sigma by D epsilon upon rho naught square root. So important point here is that this D sigma by D epsilon, this is calculated at a fixed strain value. Okay, so you end up with an equation that looks like this. And if we go to elastic region, P sigma by D epsilon is nothing but capital E, Young's modulus, and therefore Vp basically becomes C naught. So this formulation that we solved for, that we rather analyze the simple thin experiment with a weight being dropped, thin wire, sorry, the experiment of a long thin wire with a weight being dropped. By doing a simple 1D uniaxial stress analysis, we arrived at a formula for the plastic wave going through that thin wire. The same formula could be extended to elastic wave, but we basically end up with the original expression of C naught. That extension to elastic wave holds true only when the velocity of the rigid plate, this velocity of the rigid plate V1 is sufficiently small, so that so that the stress generated is below the yield limit. Okay, what this gives us is something pretty interesting. If I look at my stress strain curve once again, I could have said this is E is equal to D sigma by D epsilon at epsilon 1. And you could have D sigma by D epsilon at point 2. Label this as 0, label this as 1, and this as 2. D epsilon at point 2. This is a simple work hardening constitutive relation that I'm using. If I now plot wavefronts, this is at sigma 2, sigma 1, this is sigma naught. If I plot wavefront, what I have is, if I plot the wavefronts, what I see is sigma 2, sigma 1, sigma naught. This is my distance x, this is my stress sigma. And at t equal to t1, what have a wave that looks, it is pretty much flat. This moves with velocity c naught. This part would move with velocity c1, sorry, vp1. So move with velocity vp2. Vp1 is nothing but square root of d sigma by d epsilon at 1 upon rho naught, so at this point, and vp2 from this point is root of d sigma by d epsilon 2 at rho naught. If I plot it at another point, d2 greater than d1, sigma x, what I would see is a much more gentler slope. So vp2 is less than vp1, like this. So VP2 is less than VP1, which is less than C0. So the stress profile that you see, it will be spread out more once you go into the plastic regime, and in within that stress itself, you could have like different components moving at different speeds depending on what the particular tangent modulus rho sigma by rho epsilon looks at that particular stress. So to recap, you have upon impact you will have some particle velocity. If that particle velocity is low, you can stick to elastic wave analysis, and that is what you will get. If that particle velocity exceeds a certain limit, depending on the material, you will have plastic waves generated in that material, and that plastic wave will travel at a speed given by the tangent modulus of that material, which is rho sigma by rho epsilon. Typically, that will be sufficiently smaller than your much smaller than your elastic wave, sometimes by an order as well, which means that that high stress plastic wave front will travel slower, and your elastic wave front low stress would uh, travel much faster and reach whatever measuring point you have. So that decomposition of waves is basically, so like if you basically have a decomposition between elastic and plastic waves. There are other types of plastic waves, specifically uniaxial strain. You could also have in the case of shear, you could also have it in a 3D body. So as well as like a combined state of stress. And okay, I think that is most of it. So suppose I have sigma is equal to sigma naught plus k epsilon raised to n, which is a work hardening sort of constitutive relation. So if I do dou sigma by dou epsilon, I have got n k epsilon raised to n minus 1. So this from this you could figure out what your plastic stress would what your plastic stress velocity would look like. So Vp is root of d sigma by d epsilon upon rho naught square root of n k epsilon raised to n minus 1 upon rho. Okay, so this is how it will look for a work hardening material. We can do it for like a bilinear elastoplastic. In case of a bilinear elastoplastic material, you have E1 and E2. So when sigma greater than sigma y, your plastic wave velocity would be nothing but E2 by rho. For sigma less than sigma y, your elastic wave velocity would be root of E1 by rho naught. This is sigma less than sigma y, and this point is sigma greater than sigma. Okay, I think that covers what I had for this lecture. And yeah, do you guys have any other doubts from the lecture or from what we have discussed here? Okay, if there are none, then I'll close this session.